As Anna mentioned, I'm Marijn Bezuijen. I'm the Business Opportunity Manager for Artificial Intelligence across Shell's assets in upstream integrated gas and downstream manufacturing. In my day job, today I will be moderating this panel of very distinguished panel members. And to kick it off, I would like to give the opportunity to the panel members to introduce themselves, starting with you, Deepika.
Thanks, Murray. Good morning, good afternoon, good evening from wherever you're joining. Hello, everyone. I'm Deepika. I head the AIML division for the Smart Buildings division of Honeywell. So here we build solutions for making buildings operationally efficient and sustainable. So I've been instrumental in leading AI product development across domains like renewable energy, automotive manufacturing, healthcare, real estate, across various organizations in the past. Glad to be here today.
Great to have you. Then next, over to you, Thomas.
Yeah, hello, good morning, good afternoon. My name is Thomas, and I'm probably the least educated person here on the panel because I'm a simple operator. So up to 2 years ago, I was in charge of Linde's operations in Asia Pacific, which includes India, China, Australia, Thailand, Malaysia, Singapore, and a couple of smaller countries. And I'm here basically to give witness of being a victim of plant failures and trying to overcome this with artificial intelligence. And right now I had a business unit that is actually making this available for third-party operators that are not Linde.
Welcome. Then Satyam, over to you.
Hi, I'm Dr. Satyam Priyadarshy. I'm the Technology Fellow and Chief Data Scientist at Halliburton, and also the Managing Director of India Halliburton Center in Bangalore. I've been with the oil and gas industry for about 7 years. Before that, I was in internet and other companies. And from a background perspective, I have a PhD in quantum mechanics. And we've been developing solutions across the oil well life cycle, leveraging artificial intelligence, data-driven innovation, augmented AI for pretty much all the phases of oil well life cycle. So fascinating field to work in.
Great to have you here. Richard,
Thanks.
over to you.
Yeah, I'm Dr. Richard Xu. I'm from BHP. I'm the principal data analyst, and I have worked in both energy and mining business for over 30 years. I'm currently working in the digital factory of BHP. We try to use AI to solve any challenging and urgent problem business facing. Mainly recently, we are more concentrated on production optimization, and I'm very glad to hear. Thanks.
We're glad to have you as well. Manas, over to you finally.
Hey, thank you. Good morning, good afternoon, everyone. I'm Manas Pathak. I'm with Intel Corporation. I'm currently global AI lead for oil and gas, and I also look into the activity around Intel AI Partner Alliance. So we work with our AI partners in the ecosystem to optimize their AI solutions for Intel technologies and to bring the benefits of AI to the end user. So in this perspective, I've been working with a few of the partners in the predictive maintenance use cases, and we optimize their solutions for the benefits of the end user in the industry.
Great to have you here. To everybody in the audience, can I please direct your attention to the stage chat functionality in Hopin? Because we'll be closely monitoring that to make the session as interactive as possible. And please ask any questions on the topic of predictive maintenance in downstream applications within that chat. Either indicate who you're asking the question to, or if not, I will select a panel member to direct the question to. But to get the conversation started, I do have some prepared questions for each of the panel members that I'd like to kick off with. Deepika, first for you. If you were to adopt a domain agnostic approach to applying AI for predictive maintenance, how would you do so, and do you think that would be effective?
Yeah, so the data-driven approach we take for predictive maintenance is common across domains and across equipment. So the underlying concept is the same. So we train the machine learning model to learn the signature, the failure signatures, and the behavioral patterns before the failure occurs, so that it is able to detect any deterioration in performance of the equipment through the operational data that gets collected. However, AI ultimately has to solve a problem which is relevant to the domain. And domain understanding becomes very important for selecting the right data parameters for the asset health assessment. So typically, the expectation from an AI solution is that it has to be scalable, it has to be generalizable. So a predictive maintenance solution which has been built for a certain device is expected to work seamlessly for similar equipment across the globe. But in reality, it doesn't work that way. So there are environmental factors which affect the operations which need to be considered. These could vary across various geographical locations. There could be also multiple other factors which affect the operations. So, although at the most fundamental level, AI solutions for predictive maintenance can be domain agnostic, customization and domain adaptation are key for them to be effective.
Great. Thank you, Deepika. Thomas, over to you. And hopefully an easy question for you. How do you feel that predictive maintenance can support a move to remote operations?
Yeah, I mean, let's say we had the problem that, let's say, we do a lot of maintenance activity, or originally we did it based on frequency-based trigger. So every 3 years we take a compressor apart, or a column, or a plant. And so one thing that we were struggling with is that basically let's say these activities require a lot of planning, and on the other side, they are it's not very easy to replicate it, and we felt that we were wasting a lot of money. And so basically we went down the road of saying, okay, can we predict failures so that with a reduced manning on site, as we are remote operating our plants, we know when something is happening, because we won't have a full-fledged crew on the site at every point in time, because we move the maintenance crews around. And so predictive maintenance helped us to basically be prepared so that we could mobilize a maintenance crew or a maintenance contractor, or build the scaffolding, whatever was necessary. So that basically we would not get surprised because something fell over at 2 o'clock in the morning and we had nobody on site.
Great, thank you. Satyam, data-driven approaches are maturing quite well at the moment. Given that, what will it take to deploy predictive engines at scale in the downstream industry?
Yeah, so the maturity, I think, is a relative term. One is certainly on the predictive domain. A lot of physics-based models have been pretty mature, right, in that sense. But at the same time, as Deepika said, like, the real-world situation is very different. So in order to really integrate the data from the field, that portion of data flow, I think, still is not very mature when you compare to some of the native data-driven companies, which really know how to connect the data sets from multiple places at the same time. For example, sorry, one of the biggest challenges that you see in oil and gas industry is that these aggregation centers, which are on the field, their timestamps probably doesn't match with the sensors timestamp, and a lot of data quality issues are generated from it, and hence these kind of fundamental issues that have to be addressed in order to really build a predictive engine that can one day be called a generic engine for a similar kind of sensors or equipment. And the second part is how fast can we actually deploy the edge computing paradigm in a more robust and a scalable manner. That will be actually the one of the best things for oil and gas industry, irrespective of the stream we are talking about. And the third is a lot of training needs to be there. One assumes that if an AI model is there, it automatically will help us scale it, but that's not what the case is. You have to really do a lot of what I call the talent transformation aspect associated with it, how to integrate with physics models where possible, or engineering models, and take advantage of it while actually building completely data-driven solutions.
Thank you. And building on that, Richard, what do you think is the impact of AI on predictive maintenance?
Okay. First, the AI make predictive maintenance relatively easier because we have much more different kind of tech methods that can utilize, and also AI can process a lot of more data, and rather than we apply one kind of model to all the different machines, now it can adapt it to individual equipment, because we can train all these different models for all different equipments rather than you use one apply to all. So you make them more efficient, more solid, and make them more productive.
Great, thank you. And Manas, can you make this a bit more specific and talk about how predictive maintenance can work for downstream assets?
Yes, of course. So I mean, if we look at the downstream, like a medium size petroleum refinery has like some 6,000 odd rotating machinery in it. And one of the major loss for the refineries in US and globally is this unplanned downtime. So stats suggest some $6 billion loss in revenue in the downstream sector just because of unplanned downtime in US alone. So what can we do about it? If you look at these rotating machineries, they produce a lot of the vibration data, and there is a lot of temperature anomaly that can be detected, and the pressure data and the flow data that is being recorded with the advancement of IoT sensors. So, bringing the operational and the environment data, as well as some of the vibration data from the machinery, a machine learning model can be built to predict when a problem or a fault in a machinery can happen. Now the beauty is that if you could do that, number one, you increase the asset longevity, right? Because you predicted before the asset went down. Number two, you increase the uptime of the refinery because you did not need to stop your production in order to fix the machinery equipment. Now, if you look at where all rotating machinery go in the refinery, you have these compressors, you have pumps, you have these boilers, and these steam turbine generators and gas turbine generators, and so forth and so on. Like I said, 6,000 machinery equipment that are rotating in the typical mid-sized refinery. So hopefully that clears up what's the advantages and where all predictive maintenance can play a role in the downstream asset.
Yeah, great, thank you. And since we're talking specifically about downstream, but Satyam, your company has a lot of experience, of course, also in the upstream and the midstream energy sectors. What lessons do you think are transferable from those arenas to the downstream industry? Satyam, I'm not sure we can hear you.
So what I was saying is that one of the biggest lessons that we have learned in last 6 years, I can tell you, is the deployment of a hybrid cloud solution, which actually accelerates the pace of developing these solutions, predictive models, at a much faster pace. For the following reasons, right? One, you can now aggregate data which was very difficult to aggregate when they are in different silos, so to say, or in different storage areas of different kinds. Second is that there are like things that you never thought that could impact the predictive power of any of these equipment failure, or any of the sensors, or even data which was not related directly or not collected directly is now accessible to you. The third is like when you build these models, you can actually now scale these models much faster, because you can try ensemble of models and then bring on these what you call the predictability to a higher degree. And those same things can be really applied to downstream, especially as Manas was mentioning, right? 6,000 or 60,000 rotatory equipment. If you look at it, which is a great place for building some unique and very what I call the best AI models in that area, because the amount of data that is being collected can be collected through sensors or IoT sensors can be actually significant and can be done in real time. And that bringing that value to real time is the key part, right? As we say, what we have learned is time to value from the data is the most important part in this whole game of AI and transforming the industry.
Great, thank you. We're starting to get a couple of questions from the audience, which I think is really, really good. And Deepika, I'd like to direct the first of those questions to you, and it's specifically on performance measures to test machine learning models for predictive maintenance. How do you make sure that those performance measures are good? Because as Florian Carl in the audience asks, the standard measures seem to be inadequate because of misclassification costs, but in-depth domain knowledge would be required to quantify the cost associated with a failure. What would be your views there?
Yeah, so typically the metrics that we use are the MTTR, MTBF, that is mean time to repair, mean time between failures, the uptime. So whenever we have any predictive maintenance in place, it also has additional advantages. It brings about operational efficiency. So typically the way we compare or benchmark is before the adoption of such a solution, what was the kind of operational efficiency, or what was the MTTR, what was the MTBF, what was the uptime. And post the adoption, we do this comparison. So that's typically how we measure the efficacy of any predictive maintenance solution.
Great, thank you. And Richard, can I possibly ask you to comment on that as well and share your views how you implement this?
Okay. Sure. We commonly work with the business. We'll develop the KPI before we do the implementation, and after that we'll do a check. And because of the performance, like I say, okay, the other panel member also said, like use a hybrid deployment, because let's see, if you deploy your model onto the edge, it's different from you deploy the model directly into the cloud. The performance will be very different. So you commonly want to check all different situation to see which performance will be better and give you, the quick reaction. And also, it's how to say, make sure it's really give you the critical time so you can react or pro-react. So the performance we check, it is based on the business requirements, based on how you deploy it, and then we have the predefined KPI to do the measuring. I hope that answered the question or not.
I think it did. But Florian, do please jump in the chat if you don't think so. Thomas, I'm gonna direct the next question at you, if that's okay. Do you feel that there's any technologies that are missing from the predictive maintenance models? And William Fazarkli in the audience asked this question, and he's asking, hey, we now have pressure, temperature, vibration, and wall thicknesses measurements, but do you see any gaps, and where would they be?
Yeah, I mean, we were struggling that, let's say, there were a lot of tools that can basically work on a time series, on an average vibration, temperature, and pressure. What we saw is when we wanted, we had a lot of problems with rotating equipment, motors, pumps, compressors. And we saw that, let's say, if we want to understand what is going on, we need to be able to process more complex data like vibration spectrums. And this is actually the part that we were missing. So we basically went on and developed a pattern that basically can look at the waterfall diagram and can identify the shape of the mountain that this waterfall is producing, and can then identify, does this mountain look okay, or is there any slope or any peak in the mountain that would indicate that there's a problem? And this is basically a part that I would love to be able to buy.
Great. Thank you. Then I'm going to redirect the next question at Manas, if that's okay. Manas, Christian Oram in the audience asked a question that we spent quite a bit of time making data previously logged in spreadsheets and paper available digitally. How would you cross-reference that data with data gathered by IoT solutions that are getting more and more common in our industry most effectively?
Right. So, I mean, we have plethora of data these days, right? I mean, people don't talk about big data. What is more useful today is the useful data of the big data. So the subset of the big data that we have, which is useful for the model building, which is relevant for the business value, to bring the business value out of the machine learning on AI. So the cross-reference, I really hate to see data that you have captured over the years, the historic data, the legacy data that you would not use just because you have a different stream of data coming for the IoT, from the IoT side. So ideal way would be start with some sort of physics-based model that is noise-free, maybe a simulated data, then bring on your legacy data, historic data, to retune or refine the physics-based AI model that has been trained on physics data. So now you have physics embedded in the model, and then you had legacy data collected from the field embedded in the model, and then you deploy it. And as your new real-time IoT data stream comes into, you have what you call at training at the edge, right? So there is a new realm of training which is called federated learning. Basically, you capture the data at the edge, at the source of the data production, and you retune, refine your model or your hyperparameters in the model by the new recently captured data. So that way, your model is basically progressing from physics to real-time data collected at the edge, and with that, hopefully, the model is also increasing in accuracy, in performance, and able to predict more of the events quicker and correctly. Now, if you do deploy federated learning, what it does is basically generalizes your model. So if you have an asset A setting in Australia, you have a similar asset A setting in US. If you deploy federated learning kind of training for these models, then these models are trained with the data collected at both US and in the asset location in Australia, and the model is more generalized. It can predict the upcoming failures in both the asset locations.
Perfect. Thank you for that. And thank you, Christian, for asking the question. I'd like to direct the next question at Satyam, if that's okay. And that comes again from William. And that is, what percentage of the data used in predictive maintenance models is traditionally nice to have, like non-process critical data like vibration, and what percentage is there's a process critical data?
So, great, excellent question. I don't think there is a rule or a physics principle which will tell you that you have to have X% of data for this type and then that type, right? What is more important is, like, can I actually predict, or can I actually look at the behavior of the operation that we are doing, and is in the to actually be able to predict that from the historical data, you would actually get a sense of what percentage of data, non-operational and operational data, is needed, and then you scale it up. So if anybody says that I will use 10% of operational and 20% of non-operational data, I don't think it works that way. The best thing to look at is, if you have historical data, leverage maximum amount of it from operational side as well as from non-operational side, because that will give you the biggest possible, what in the marketing term people call it, behavioral model. And from that model, you can actually decide, in order to really go forward, under what conditions this model will give you different predictions, put the boundary conditions on that model, and that will actually define you like what other data sets that you should be collecting in the future, and how do you like integrate those data sets, and that way you can build a scalable system. The other just before this, there was a question about how much data and how do you like validate the data sets. I think on that one, the one comment is that, if we are collecting data from IoT sensors, then raw data should always be kept rather than actually modified data, because when we are building AI models, if the quality problems are there, people will actually modify or delete outliers or whatever they do, which is probably not the best practice, but at the same time it makes life easy. So keeping that raw data which is tagged properly with the correct data governance within the data governance framework is very, very critical if you ever want to reproduce the results.
Great, thank you. And Thomas, I saw you were smiling when the question was asked, so I assume you have a view as well.
Yeah,
would you mind
exactly.
sharing your view on that?
Yeah. Basically, I mean, we had a very simple method, and let's say I had, as I said, I was in operations, and a couple of digital guys were chasing me and said, Thomas, we think we can predict failures of your compressors. And I said, I don't believe you at all. And so we made a very simple data validation exercise. I said, so we have about 10 years of operation data for each of our machines, and pretty much everything we record. And so I said, look, I give you 3 years of operation data of 10 compressors. And if you can tell me which of the compressors had a problem afterwards, then you have a deal. And surprisingly, and I was sure I could fend them off because they wouldn't predict anything that would happen after this when the data was cut off. Unfortunately or fortunately, let's say we had actually 2 compressors that had a problem. They identified the 2 and they found one more which was incorrect. And so basically what we would do is we would basically take the view of a pathologist to say, look, when we had a failure afterwards, we would use the data that we have recorded and run the model backward and say, okay, so would the model have identified the thing that has happened?
Great, thank you. The next question I'm going to direct at you, Deepika, because I know you have some expertise in this area, and that is how do you get the relevant data on the failure of the machines? They don't normally run to failure. You don't really get a lot of data there on failures. So there wouldn't be a ton of data on these failures. This is a question from Florian Carl again in the audience.
Yeah, so the harsh reality is that maintenance data mostly is not available. And even in cases where it happens to be available, it is not digitized in many cases. So this means that we do not have the signatures or behavioral patterns of equipment before it failed. So in such scenarios, the approach that we take is we train the machine learning models on only the normal behavior of the equipment. So once the machine learning model learns the normal behavior from the operational data, if it spots any behavior which is deviating from what it has learned, which is normal, it will automatically trigger notifications or alerts saying that there is an anomaly. Right. So yet another approach that we look at is comparing similar equipment which are operating under similar conditions, and their behavior is compared. If one of them happens to behave very differently from the rest of them, then that again is an anomaly for us. So in order to deal with this issue of the lack of maintenance data or the past failures, we have a combination of these kind of unsupervised and supervised techniques from machine learning perspective.
Perfect. Thank you so much. Richard, I'm going to direct the next question at you, if that's okay.
Sure.
When you're collecting data in a predictive environment, what criteria would you use to determine where a preventative approach might make more sense, if that would allow you to improve scheduling and resource availability forecasting?
So it means one, we should use predictive maintenance.
It's really on predictive versus preventive, and when would you use the data to improve your preventative maintenance rather than deploy predictive maintenance?
Maybe I'm biased. I'm more towards predictive maintenance rather than preventive maintenance because, from my experience, we feel it's always this way. It's save you money, and also it is, condition based rather than time based. So it reduces cost. I didn't see a situation where I wanted to use preventive rather than predictive. Maybe I'm more biased. Sorry.
Yeah, I think, Marin, I would have a very simple answer. If you don't have enough money to do preventive maintenance, do predictive maintenance. Because I think I tried it myself. So I went from completely time-based to completely diagnostic-based. And this allowed me to, I reduced my maintenance budget by about 30%. Because
Yes.
typically you have the OEMs who tell you, of course you have to take your machine apart every 3 years. You have to change all the bearings and everything. But it's mainly driven by driving their after-sales business, not necessarily by helping me as an operator. And I think this predictive part can get us as an operator out of this trap that you have an OEM who tells you, if you don't do that, the machine is for sure going to fail.
Great, thank you. And Manas, maybe for you, what do you see as the end goal for predictive maintenance? Do you see these in the hands of operations, of inspection? Do you see a global team that specializes in the modeling do this? Where do you see with your projects and your customers, where do you see this ending up typically?
Right. I think so. One of the things that came up earlier as well was the domain expertise. So definitely we would need a lot of the subject matter experts in the team who are deploying these models. Sometimes I say these AI and machine learning models is not about when it comes to these domain specific use cases. It is not about predicting what next movie you want to watch based on your history of watching movies. So definitely we would need a lot of subject matter experts in the team along with the data scientist. Moving forward, 5 years fast forward, you're gonna see these AI and machine learning would become just as a tool for the otherwise subject matter experts in the domain. So we have all these SMEs and the vertical domain scientists. They have been doing this kind of job for many years. So machine learning and AI would become just yet another tool for them to do their job better. Now, if you look at the deployment scenario, I think the more and more general we make these AI models, better it is. So like I previously mentioned, there are possibly merits in the data collected in asset location A that could be used for better predictive maintenance of same asset A, but in a different location, say B. So this kind of data aggregation is ideal. Now with cost of cloud computing and everything else, like the bottlenecks of accumulating and aggregating data from different locations, what may happen is federated learning, basically training the model at the source of the location. So there is a one model that's sent to the different asset locations, the locations of the same asset across different geos, and then that model basically learns on the operational data and the environmental data of that asset at that location, and then it's basically becomes a better model in the iteration. So a very good example I use is wind turbines. We have wind turbines in US offshore, we have wind turbines in Europe offshore. If the same OEM can deploy a model that's trained on both the US offshore and the US Europe offshore's wind turbine operations and the environment data, it's just a better model. So hopefully this is where we will eventually end up in the future.
Thank you, and Satyam, since you work with some of the biggest players in the industry, I'm going to ask you a similar question as well, based on William's question. Where do you see that the industry is moving? In whose hands do they put these models? Is it the operators, is it engineers, is it inspectors, or is it a central team somewhere that has expertise in machine learning?
So the way we have approached, I'll tell you how we have done for the last 7 years, and it has worked well for us along with our customer partners, right? So we have what is called a center of excellence for building these models and basically propagate the knowledge across the industry or across the company as well as across the industry. So that way you have an awareness of like what kind of models and what kind of data is used for what kind of models and where it has been applicable, and so that you don't actually do duplication of effort. Like one of the biggest challenges we have seen in our industry is that a lot of duplication of effort goes on, and that is still a cost if you want to think of it that way. And second is that we do things which don't integrate when you are doing in silos. So the being the center of excellence actually enables that communication, and as a result the team can be diverse, right? Now the two part of the challenge when it comes to deployment, especially in oil and gas industry, and I'll give some example from upstream. You While a model is ready, and in a common terminology of AI, people will say, is my model production ready? Now production ready in oil and gas industry is slightly different. What I call it, it has to be field ready. So that requires a significant amount of validation before you can actually take it to the field. And then of course the whole model lifecycle management has to be in place, similar to data governance. And these things are important while we want to accelerate the pace of developing these models. But model lifecycle management itself is a challenge, because it's a completely new field to the industry, and we respect it. It is irrespective of the stream, again, nothing to do with the upstream or downstream. And I think that is some of the practices for that we propose certain frameworks under which we actually use. Is that how much of the validation is needed? I think our friend Thomas was talking about the case study when he said three pumps or 10 pumps. This scalability is very, very important before you actually can take it to the field. And it is critical. What we have seen, it is for the same manufacturer deployed in the similar environment, but the data that is being collected is very different. These are people have invested millions of dollars restoring this data, but one model that would work, say, in Middle East is not likely to work in Latin America, even if it is the same equipment from the same manufacturer, and maybe exactly the same model that we have seen. But the question, because the data collection methodologies are different for the organizations, hence this concept of center of excellence, which keeps the knowledge in one place and shares that, makes it very easy between sharing with data scientists and data engineers and field engineers and operational experts, and of course the leadership.
Great, thank you, Satyam. And then William asked a follow-up question around how do you encourage end users to trust the model, especially aimed at experienced operators. And Thomas, since you're probably the closest to an experienced operator we have, how would you encourage your end users to trust the models?
I mean, there is a systematic way or unsystematic way. I mean, one thing that happened while we were deploying these models, or basically 4 weeks after we had deployed the model, we actually had a diagnostic alarm that prevented a major damage of a generator. And this, of course, before nobody believed us that we would be any good. And of course, these kind of, let's say, individual cases where you can show that this is actually real. And, once you open the machine or you open the furnace or whatever you're monitoring, what the prediction said is actually happening. And so this was something that unfortunately you can't plan, because you can't really you don't know whether this events happen, but this was basically the biggest part. And so we were using that as to showcase what it can do. But you can be unlucky and basically nothing happens for 6 months, and everybody says, Thomas, why did you waste all the money? However, what we saw is that the other part was that, let's say, when we were able to do predictions for the next turnaround, I mean, typically you have to plan 5 or 6 years ahead of what you want to do. And so the other possibility was to convince them by, let's say, changing, let's say, from this time-based or preventive maintenance to the diagnostic-based or predictive maintenance, to make predictions of, you know, which parts would you need to change, but maybe go for the full turnaround scope and open the machine, even if the diagnostic said there's nothing, just to confirm that there is nothing and that you can trust the prediction.
Great, thank you for that. Hey, we still have time for a few more questions. What I'd like to do is take the conversation in a slightly different direction and look at sort of the current reality. And Deepika, I'd like to ask you a question. So, of course, we're still in a pandemic. This shouldn't last forever. What do you think that the post-pandemic world would mean for something like predictive maintenance?
Yeah, so the pandemic has rendered digitalization and remote monitoring imperative across industries. So minimizing the human intervention is the need of the hour. Right? So and condition-based predictive maintenance solutions are not just good to have anymore; they are a must-have. So the pandemic has in fact helped prove the value of these solutions, and domain experts now understand and have accepted that this is doable, and have also clearly seen the value, and have these solutions are proving to be much more cost effective. So predictive maintenance solutions will only be more widely adopted in the post pandemic world.
Great, thank you. And on a vaguely similar but still very different note, another key development, of course, is the energy transition that we're all going through. And Satyam, a question for you: in that energy transition era, how far can we go with predictive analytics?
I think, especially for oil and gas industry to remain a critical and important player, predictive maintenance, and I think going one step beyond predictive, which is building prescriptive engines, will actually make oil and gas industry very relevant in the energy transition landscape, because this landscape is going to be very complex, especially if you look at the recent studies with wind energy and solar energy and geothermal. They all, if you look geothermal and oil and gas, some of the operations are similar. But if you look at the overall picture of these four major, at least energy sources, I think this the predictive and the prescriptive engines will play a role across all these energy sources, and hence building these models as quickly as possible and as robust as possible is very, very critical. So for each of these energy source methods, and you can see that what happened in Texas can give you an example that if you look at the modeling behavior, I don't think ever somebody put a temperature from the weather as a equipment failure metrics, and now you can see that some of the data that we never collected could actually go in these models. So one has to think beyond what the traditional data sets we have been collecting for predicting these failures. You have to really look beyond it.
Yeah, and I think, Marian, there is another one. Let's say I'm just coming out of a discussion this morning within a large oil and gas company in Australia, who is the second largest energy supplier there. And I mean, what they struggle with, they're going through this transition currently. And what they see is, let's say, from very large sites and big units with a lot of staff, you're moving to many, many decentralized units, and all of a sudden you don't have enough people who can basically hear and knock with a screwdriver against something to see whether something happens. And they basically, their drive for predictive maintenance is that they say we get more and more decentralized assets in the middle of nowhere, where, let's say, we don't get critical mass with an operation team. So can you help us with the predictive maintenance to basically kind of control all the ants that are crawling around?
We just got another question specifically aimed at you, Thomas. What do you think is the main driver behind developing your models in-house? And how would you make the choice between what you do in-house and what you do with third parties?
Yeah, the main driver was very simple. When I arrived in Singapore, this was shortly after the financial crisis. My boss said, you have to reduce your maintenance cost by 30%, cut your staff by 25%, and increase the availability. And basically, I mean, without predictive maintenance, it seems this is impossible. So that was my drive. So basically, I needed to reduce my staff. I needed to be more reliable, and I didn't have that much money. And basically, what we did is we said, okay, we have no other chance. Let's try it. And I mean, the result was that basically the unplanned maintenance cost went down by 50%. The staff was reduced by 30%, and our reliability went 2 points up.
And specifically, what made you do that in-house versus going to a third party?
We wanted to buy it because, as I said, you know, I wanted to operate. I'm not neither a supplier nor an IT guru. So in principle, we went to the large companies. You all know them, GE, Aveva, whatever they are called. Which we did large trials. We got lots of promises, and actually nothing really worked. And basically, the problem was that, let's say, the effort to maintain the models was so high that my expert said, "Look, Thomas, just throw away the model and let me look at the raw data. This is as much work as if I keep on tuning the models." And at that point, we went out to an AI company who is specialized in the industrial space. And we said, look, this is what we want. So we want a model that is self-tuning through reinforcement learning. So I don't have enough staff to keep on changing the equipment because the equipment is aging or our operating conditions are changing. So can you build us basically a predictive maintenance that is maintenance free? And because we couldn't, so I would have loved to buy it. I tried it. I completely failed and was very disencouraged, or my team was very disencouraged. And then we said, okay, let's go to a specialized company, let them exactly tell what we want, and we want a maintenance-free algorithm. And this then ultimately gave us the possibility. The second part, and Satyam, I think you were talking about the Center of Excellence. We were very much worried that we would implement with some of these big names. They would drop something and would leave us alone, and 6 months later, nothing would work. So I think one key aspect, and I think Satyam, and it doesn't really matter whether you do it in-house or with an external partner, but if you want to keep these things alive, you need a long-term relationship with the people who have developed it, who, number one, adapt it to whatever your operations reality is, and it's constantly changing, at least in Linde. And number two, let's say, keep the ball rolling, because I mean, with better algorithms, with better methods, with more sensors that come along, this journey never ends. And let's say, typically, I mean, we have the task to get 5% more productive every year. So this means we can't stop. And so I think for me, the key part is that you have a partner that is with whom you have a long-term relationship, and say, in 5 years or in 3 years, I still have access to the method and to the know-how.
So let me add one comment
Final
to
remarks,
that.
Satyam.
Yeah. So what we have done in the last 6-7 years is we built this method called perfectly for Thomas's question or a comment, that we actually use a method called co-innovation. So in fact, while we are a service company, when we build these models with our customer partners, we actually train those people in the details of these models and what's going on, so that when there is a need for a minor change, and if that expertise is there in-house, they can do it. So they don't have to really rush to a service company or anybody saying, oh my God, we need to change this. But the goal is to increase and scale these models as fast as possible, so that many of these challenges can be addressed. So that's why this knowledge sharing, not just within the company, that center of excellence I'm talking, we actually did this through co-innovation with even our customer partners, because that is how this industry can actually benefit and actually be resilient.
Yeah,
perfect. Thank you, Satyam. And with that, Thomas, sorry, I'm going to have to close the panel. I'd like to continue the conversation as well with each of you, actually, but there are more interesting panels and topics coming up in the conference. So thanks a lot for your insightful answers. I really appreciate that you responded well when I put you on the spot, everyone. Really good discussion, and thanks to the audience as well for asking interesting questions. Really appreciate it. Take care.